Good morning. This is a new video about this second unit of descriptive statistics. In this video, we will talk about frequency tables, about histograms, and about the concept of density function. Okay, so first, frequency tables. This is used for the case of discrete variables. For example, imagine that I ask a group of 34 students to think a digit at random, a digit from 0 and 9. Okay, so every student has to think a digit, and then the information can be summarized in this table. Okay, so for example, the digit 0. Imagine that no students chose this digit. The value 1 was chosen by 2 students. Okay, in this example, we have number 2, which was chosen by 6 students, number 3 by 7, and so on. Okay, so this is called the number of occurrences and is also called absolute frequency. The absolute frequency is the result of counting. So how many values do I have for 0, 1, and so on? So if I sum the values of the absolute frequency, in this case is 34, because I had 34 students who answered this survey. Then I can divide every value by 34, and then this becomes the relative frequency. For example, I have 6% of students who chose the digit number 1, or I have 21% of students who chose the digit number 3. Okay, so this is relative frequency. Then what happens in a continuous variable? Can I use this kind of frequency table? The answer is yes, but before I have to group the values within intervals. Okay, so this is an example. Imagine that I have values for the resistance of a given polymer. Okay, and then I make the following intervals from 10 to 15, from 15 to 20, and so on. The last interval is from 70 to 75. Okay, then I count the number of values which were included within every interval. Okay, for example, between 20 and 25, I have 9 values, or between 25 and 30, I have 18 values. Okay, good. This is absolute frequency. If I sum, in total, I have 174 values. So if one of these values is divided by 174, I will have the relative frequency. For example, here I have that 5.5% of the values are comprised between 20 and 25. Okay. Then another concept is the concept of cumulative frequency, okay, that we can find here. Cumulative frequency, what is the concept? Okay, so we are accumulating the values in the following way. So we have 0, and then 1 plus 9 is 10, so here we put the value 10. 10 plus 18 is 10 plus 18 is 28. Yes, 28 plus 26 is 54, and so on. So that the last value of the absolute cumulative frequency is the total number of values that I have. So what is the interpretation of this value 28? So that would be the number of values that are comprised between 25 and 30, or in previous below intervals. So it is the same as saying the number of values which are less or equal to 30. Okay, so this is the interpretation. And then finally, we have the cumulative relative frequency. So we take these values and we divide them by 164. So the last value of the cumulative relative frequency is always 1. What is the interpretation? For example, this value is 17%. I will say that 17% of the values are comprised between 25 and 30, or below this interval, which means that 17% are below 30. Okay, so this is the interpretation of the frequency table for a continuous variable. Good. Okay, so this is the example that I was describing. Now imagine that we focus on these values. Okay, and then one exercise that often I ask to my students is to represent these values graphically. Okay, so on the horizontal axis, we represent these values, okay, from 10 to 15, 15, 20 until 75, and then on the vertical axis, we represent this absolute frequency. Okay, what happens if we make exercise? So it becomes a histogram. The name of the plot is called histogram, which is a very important diagram that we use in statistics. Okay, a histogram is a graphical representation of a data set. The minimum number of values is usually 40 to 50. Does it mean that I cannot make a histogram with less than 40? Yes, we can. We can make a histogram with even 9, 10 or 15 values, but the information that we get if we have very few values is very poor. Okay, so the recommendation to get a useful information from histogram is to have more or less at least about 40 values. Okay, so this is a picture, a general picture of a typical histogram. Okay, here in the horizontal axis, we represent the intervals. Okay, so then, for example, from 15 to 20, 20 to 25. Okay, and in the vertical axis, we represent the number of values that we have inside every interval. Okay, so this is a common shape. Okay, usually this shape that resembles a bell is very common and is called a normal distribution. Okay, this is something that we will repeat many times in this unit of statistics. Okay, this normal distribution is the most common in practice. Okay, so in the vertical scale, we can here, okay, we can represent absolute frequencies or relative frequencies. And then again, one exercise that I often ask to my students is, in this particular case, is it absolute frequency or is it relative frequency? How can we know that? Well, we have to sum or to add the height of the different bars, okay? So in this case, we get a number higher than 100. It means that it is absolute frequency. Okay. Then, in this particular case, it seems that more or less the shape of the histogram is approximately symmetric. And then, in this case, we will say that the distribution of the values is symmetric. And this is a very important idea. When we say that data follow a symmetric distribution, it means that if I make a histogram with the data, the shape of the histogram is approximately symmetric. If I say that my data follow a non-symmetric distribution, it means that if I make a histogram, so this histogram is not symmetric. Okay? Well, another important issue when we want to build a histogram is the number of intervals. This is something that we can change, okay? And many people think that the higher number of intervals, the more information that we get from histogram. And this is not true, because the target of the histogram is provide a description, more or less, about what is the shape, the general shape of the distribution. For example, is the shape symmetric? Is the shape clearly not symmetric? And so on, okay? So imagine that I build a histogram with just 3 bars, okay? This is very poor. The information that I will get is too poor, is not useful. But again, if I have 100 data and I use 50 bars, it is too much. Again, the information that we will get from this histogram is not very good. So there is like a rule to recommend more or less the best number of intervals. This rule is the square root of n. Okay, so this rule works more or less good. And my recommendation is that every time you have to check the interval with different number of intervals to see which one provides the better information. Okay, so for example, imagine that I have just 9 values. The square root of 9 is 3. So it means that I can build a histogram with just 3 bars, but the information is too poor. This is why the histogram, to get useful information from that, requires at least 30 or 40 values. Okay, then now I'm going to show different shapes of histograms. For example, this is an not symmetric or asymmetric histogram. In English, we will use the word skewed. This is a word that I will use quite often, okay? So when I say a skewed distribution, means that if I make a histogram with the distribution, the shape of the histogram is something like that, okay? So important term in English, skewed distribution, okay? There are two types of skewed distributions, like the one that I'm showing here in the slide. It is called a positively skewed distribution or a distribution with a positive skew, okay? And here is, well, the opposite, of course. If I invert the shape of the picture, it would be a negatively skewed distribution. Okay, so here is a special type of histogram, okay, because I would expect to find values here, but there are no values. So probably the reason is that those values were removed. And then in statistics, it is called truncated data. Okay, for example, imagine that I have the scores only for those students who passed the exam. So if I make a histogram with the values, so I would get more or less something like this. It is called truncated data. So those values in red were removed. Good. So this is another example. This histogram is revealing something strange, because the shape looks like a bell, looks like a normal distribution, but here the frequency for this bar is much lower than expected. So, but the next bar is much higher than expected. Okay, so it seems that this bar should correspond to the left. Okay, so here it's revealing some kind of abnormal frequency, maybe due to a systematic error in the data recording. Okay, so another usefulness for this histogram is to identify mixture of populations. Okay, it may happen quite often. So imagine, for example, that I have data from one population and it is symmetric, more or less it follows a normal distribution. And then imagine that I have also data from another population with a different average, okay? So the data from the first population range more or less from here, the minimum, to here, the maximum, and then I have the data from the other population with the minimum here and the maximum here. So next, imagine that I have the data mixed in a single column of values, okay? Now, what happens if I make a histogram with this single column of data? So I will have a histogram like that. So the shape is like this. So the frequency increases, it goes up, and then now it goes down, it goes up, and it goes down. It is the typical shape of a histogram revealing a mixture of two different populations. Sometimes it is called bimodal distribution. The mode is this relative maximum, so this would be one mode. This would be another mode. So it is a distribution with two modes, and this is why it is called bimodal distribution. So in this case, the mixture of two populations was very clear. In some other cases, it is not so clear. For example, this is more or less a symmetric distribution. It also corresponds to a mixture of two distributions, but it is not so clear as in the previous case. Okay, so a flat histogram may be indicating a mixture of two populations with a similar mean. Okay, sorry. Now, an important concept that we have in statistics is called density function. This is only for continuous variables. So, mathematically, to define the concept of a density function is not easy, okay? So usually, the easiest way that I say to define a density function is that it is the mathematical function that describes the shape of the histogram, okay? So I like to give a relationship between histogram and density function, and this is why I'm explaining this concept here. So, for example, imagine that I have values of time recorded by an algorithm to invert a matrix, okay? Imagine that I have these values, And then imagine that I have 40 values from this time, and then I make a histogram with them. Okay, so remember that usually in the vertical scale, I represent the absolute frequency or the relative frequency. This histogram is a bit special because the frequencies are indicated according to the area. Okay, so for example, the area of this bar is 15% of the total. This is 14% of the total, and so on. Okay, so if I sum the area of the bars, the sum is 1. So it's like a common histogram, but a bit special for this reason. Okay, so now imagine that the sample size increases too much. So now instead of 40, I have 40,000. Okay, so as I have so many values, I can have many bars. Okay, so I can reduce the width of the bar, and then quite often I can have a histogram more or less with this shape. This is the shape of a bell. It is called Gaussian bell. It corresponds to the normal distribution. Okay, the norm model is something that I will explain in further videos, but it is important that to talk about this from the beginning, because the normal distribution is very important, because we often encounter this distribution. So again, what is the percentage of values that are comprised between 30 and 40? Okay, what is the probability to find a value between 30 and 40? In this case, it was 50%. In this case, again, we sum the area of the bars here, and this area will be 15%. Okay. Now, I imagine that instead of 40,000 values, I have infinite values. And then so the number of values tends to infinite. And then the shape of the histogram will tend to a very particular curve. Okay, so the curve will be perfectly defined and will be more or less something like this. And then the area below the curve is 1, so the percentage of values between 30 and 40, again, will be 15%. So this is the density function. Okay, so here, this line, this curve will be the density function. And the very important rule for any kind of density function is that always the area under the curve is 1, so that the probabilities are computed in this way. Well, this is something that I will explain in further videos. Okay, then another useful that we have in statistics is called a bar chart. A bar chart, for example, is something like this. It looks like a histogram, but it is not. It's quite different. For example, I can have the frequency of something corresponding to different countries. Okay, for example, the frequency of people that work in certain profession, for example. Okay, and then the first bar corresponds to Spain, the second to France, the third to England, then Italy and Ireland, and so on. Okay, so it looks like a histogram. In the vertical scale, I can represent absolute frequencies or relative frequencies. But the main difference is that the horizontal axis is different. Okay, so here I can say, is the distribution symmetric or skewed? Well, this information is nonsense. So I cannot ask this kind of question, because here I can change the position of the different bars, and I will have exactly the same type of information, but obviously the shape of the histogram, the shape of this plot will change. Okay, then it could be an example of a question. No, is it skewed? Well, it cannot be answered. I cannot say if it is skewed or not, but I can check if the frequency is absolute or relative. How can we know that? We can sum the height of the different bars. If the height is different from 100, so it will say that it is absolute frequency. But if the height is exactly 100, so usually we will say that it is relative frequency. There is only one exception, unless that the number of individuals was exactly 100. So another chart that we can use in statistics is called a pie chart. This is an example. This is an example of a pie chart, and I usually say that this is the typical chart of the elections. Okay, so when we have a general election, usually the percentage of votes for the different parties are expressed and very common in a way like this. Okay, because graphically it represents the differences in the percentages. Okay, so when the key issue is to express visually the differences in percentages, so this is a good option. Okay, so well, here I finish this video about frequency tables, histograms, and density function. Thank you for your attention.